Welcome all. This is lecture number 8 on vector integration. In this lecture, we will discuss Gauss divergence theorem. Gauss divergence theorem means relation between surface integral and volume integral. So first question arises, what is Gauss divergence theorem? Gauss divergence theorem means the surface integral of the normal component of a vector function vector f taken around a closed surface capital S is equal to the integral of the divergence of vector f taken over the volume capital V enclosed by the surface capital S, that is double integral S vector f dot n cap ds is equals to triple integral V divergence of vector f dv, where n cap can be defined as cos alpha I plus cos beta j plus cos gamma k, which is the outward drawn unit normal vector to the surface capital S. So this is the formula or the relation of surface integral and volume integral, and which is known as Gauss divergence theorem. So we are taking examples. So example 1, find double integral S vector f dot n cap ds, where vector f equals to 2x plus 3zi minus xz plus yj plus y square plus 2z k cap, and capital S is the surface of the sphere having center at 3 minus 1 2 and radius is 3. So to solve it, we let capital V be the volume enclosed by the surface capital S. Then by Gauss divergence theorem, we have this particular formula, double integral S vector f dot n cap ds equals to triple integral V divergence of vector f dv. So we can find this divergence of vector f. We have to find this, and this is converted into the triple integral V divergence of vector f dv. So divergence of vector f is del dot vector f, and del is I del over del x plus j del over del y plus k del over del z. Dot product with vector f is this. So right here 2x plus 3z iota I cap minus xz plus y j cap plus y square plus 2z k cap dv. So what is the dot product? When we make dot product, then I dot I, j dot j, k dot k are 1, rest are 0. So del over del x of 2x plus 3z, del over del y of minus xz plus y, so take minus outside here, and del over del z of y square plus 2z dv. So partial differentiation of 2x plus 3z with respect to x is 2, because this is 2 and this will be 0. Partial differentiation of xz plus y with respect to y is 1, because xz is a constant, so it is 0, and the partial differentiation of y is 1, and same as here we take 2. So it will be 2 minus 1 plus 2 dv. So 2 or 2 4 minus 1, that is 3 triple integral v dv. Now this is the formula of volume. So the volume of dv is v. So it will convert into 3v, and we are talking about the sphere. So what is the volume of the sphere? 4 by 3 pi r cube. So we write here, and what is the r? R is the radius, and radius is given, which is 3. So replacing r by 3. So here this 3 is cancelled out, and here 3 cube is 27, and 27 4 ja 108. So the value of it 100 pi. It means double integral s vector f dot n cap ds is equals to 108 pi is the required solution for the given problem. So example 2, find double integral s vector f dot n cap ds over the entire surface of the region above the xy plane bounded by the cone z square is equals to x square plus y square and the plane z equals to 4. So the initial for the plane is z equals to 0. If vector f is equals to 4xz I cap plus xyz square j cap plus 3z k cap. So to solve it, let capital V be the volume enclosed by the surface capital S and capital V is bounded by the surface means cone and the plane. So the cone is z square is equals to x square plus y square and the plane z equals to 0 and z equals to 4. Then by Gauss divergence theorem we have this initial formula double integral s vector f dot n cap ds is converted into the triple integral v divergence of vector f dv. So put the value of divergence. Divergence means del dot vector f, that is del is I cap del over del x plus j cap del over del y plus k cap del over del z dot product with the vector f, and vector f is 4xz I cap plus xy z square j cap plus 3z k cap dv. So we first make dot product, and for the dot product only I dot I, j dot j and k dot k remains and rest will be vanished. So in case of when we differentiate partially 4xz, then 4 is the constant, so we can take it outside. So del over del x of xz and j dot j 1, so del over del y of xyz square. So we are differentiating partially with respect to y. So in this case xz square is the constant, so we can take it outside. So it will be del over del y of y and same as thrice del over del z of z. So partial differentiation of xz with respect to x will be z. Partial differentiation of y with respect to y is 1. Partial differentiation of z with respect to z is 1. So it is converted into triple integral v 4z plus xz square plus 3 dv. So now we have to integrate it over the entire surface of the region. So limit for z are given, z equals to 0 and z equals to 4. So these are the constant limits. So we can take these outside, and for the limits of x and y we use this particular cone, that is which is the surface. So in this case if we have to find the value of x, then we can write it as x square is equals to z square minus y square, so that x will converted into plus minus square root of z square minus y square, and we are talking or we have to find over the entire surface. So we take limits minus root z square minus y square to z square minus y square, and for the limit of y when x vanishes then it will be y square is equals to z square. So y will be minus z to z. So in this particular manner. So now variable limit is in y and x contain two variables. So first we have to integrate this entire function with respect to x. So now here we can apply even and odd principle, because limits are x equals to minus a to a, and if f minus x is equals to fx then even, and if f minus x is equals to minus fx then the odd. So when we put x equals to minus x here, then it will be negative, so it will be odd. So according to principle this function will vanish, so only 4z plus 3 remains. So now see, we have to integrating with respect to x. So this 4z plus 3 will be treated as the constant. So we can take it here or we can take it outside. So the integral of dx is x under the limit 0 to root z square minus y square. So when we put limit, so it there will arise is square root of z square minus y square. So the entire function will convert it into twice of integral z equals to 0 to 4, integral y equals to minus z to z, 4z plus 3 into z square root of z square minus y square dy dz. So in this particular manner. Now see here variable limit is in y. So we have to integrate this function with respect to y first. So in this particular case 4z plus 3 is the constant, so we can take it outside the integral. So only the integral of this square root function remains. So what is the integral of square root of z square minus y square? Now see, we have to integrating with respect to y. So the z square is treated as the constant. So it is square root of a square minus y square. And what is the formula? This is directly formula y square root of z square minus y square by 2 plus z square by 2 sin inverse y upon z under the limit 0 to z. If you remember, integral of square root of a square minus x square dx is x root a square minus x square by 2 plus a square by 2 sin inverse x upon a. So this is the formula we use here. So on putting the limit, when we put z equals to y equals to z, then it will be z square root of z square minus z square. So it is the 0 plus z square by 2 sin inverse 1. And when we put 0, then the entire function will be 0, because here sin inverse 0 and it is 0. So the entire function will be 0. So it will convert into this is 0. So z square by 2 and it is the sin inverse 1. And when 1 is arises in the sin inverse, so it arises at pi by 2. So it is z square by 2 into pi by 2. Now see 2 to the 4 and this 4 is cancelled by this 4. And we can take this pi outside the integral. So we can write it as pi integral z equals to 0 to 4, 4z plus 3 into z square. So we can take z square inside the bracket. So it will be 4z cube plus 3z square dz. Now this is the single integral. So we can integrate it with respect to z. So the integral of z cube is z raised to power 4 by 4 and the integral of z square is z cube by 3. And now see, this 4 is cancelled out by this 4 and this 3 is cancelled out by this 3. So only z raised to power 4 plus z cube remains. So on putting the limit, it is 4 raised to power 4 plus 4 raised to power 3. So the 4 raised to power 4 is 256 and 4 cube is 64. So 256 plus 64 is 320. So the value of this particular problem is 320 pi. So hence double integral as vector f dot n cap ds is equals to 320 pi. So this is the required solution. Moving on to the next problem. Example 3. Verify divergence theorem for vector f equals to 4xz I cap minus y square j cap plus yz k cap taken over the cube bounded by the planes x equals to 0, x equals to 1, y equals to 0, y equals to 1, z equals to 0 and z equals to 1. So we have to verify divergence theorem here. So to solve it, we have vector f is 4xzi cap minus y square j cap plus yz k cap. So to verify it, we have to find double integral directly and triple integral directly, and the value so obtained from the both cases should be same. So in case of triple integral, we first find triple integral. So the divergence of vector f is equals to I cap del over del x plus j cap del over del y plus k cap del over del z dot product with 4xz I cap minus y square j cap plus yz k cap. So make the dot product. So it will be del over del x of 4xz. Now 4 is the constant, so we can take it outside. So del over del x of xz, minus is there, minus plus minus, so del over del y of y square and del over del z of yz. So partial differentiation of xz with respect to x is z, partial differentiation of y square with respect to y is 2y, and partial differentiation of yz with respect to z is y. So 4z minus 2y plus y, so it will be 4z minus y. So this is the divergence of vector f. So from triple integral v, divergence of vector f dv is equals to, now limits are there. So we can take directly x equals to 0 to 1, y equals to 0 to 1, z equals to 0 to 1, 4z minus y dz dy dx. So first we have to integrate with respect to z. So the integral of 4z is 4z square by 2. So 2 is cancelled by this 4, that is the 2z square, and minus y z under the limit 0 to 1. So on putting limits of z, when we put z equals to 1, then it is 2 minus y, and when we put 0, then the entire function will be 0. So the function is converted into integral x equals to 0 to 1, integral y equals to 0 to 1, 2 minus y dy dx. Now we have to integrate it with respect to y. So the integral of 2 minus y is 2 minus 2y minus y square by 2 under the limit 0 to 1. So on putting the limit, when we put y equals to 1, then 2 minus 1 by 2, so it is 3 by 2, and when we put 0, then the entire function will be 0. So it is 3 by 2 integral x equals to 0 to 1 dx. So the integral of dx is x under the limit 0 to 1, and when we put 1, then it is 3 by 2. So this is the value from the triple integral. Let it is equation number 1. Now moving on to the second part of this particular verification, and the second part is the surface integral. So we have to draw this particular cube first. So to evaluate this double integral as vector f dot n cap ds, capital S is the surface which contains 6 faces as shown in the following figure, in this particular figure. Let these points are A, B, C, D, E, F, G. Now the coordinate of origin are 0, 0, 0. Coordinate of A, it is on the x-axis, so 1, 0, 0. Coordinate of C, y-axis, so 0, 1, 0. Coordinate of F, it is z-axis, so 0, 0, 1. Coordinate of V, it is in the xy plane, so 1, 1, 0. Coordinate of E, it is yz plane, so it is 0, 1, 1. Coordinate of G, it is xz plane, so 1, 0, 1. And coordinate of D, it is in the all three axis, in all three dimensions, so the coordinate of D are 1, 1, 1. So it contains 6 faces: O, A, B, C, O, C, E, F, O, A, G, F, B, C, E, D, G, D, E, F, and A, B, D, G. So double integral as vector f dot n cap ds can define in the 6 faces as double integral for the face OABC plus for the face DEFG plus for the face OAGF plus for the face BCED plus for the face ABDG plus for the face OCEF. Let it is equation number 2. So now find the value for this particular face first. So double integral vector f dot n cap ds for the face OABC. Now vector f is 4xzi minus y square j cap plus yz k cap dot product with n cap and OABC. It is in the xy plane in the downward side. So in this particular case z is equals to 0. So and the face is in the downward side, so the n cap will convert it into minus k cap, and for the xy plane ds is converted into dx dy upon mod of minus k cap dot k cap. So it is the 1, and when we make dot product then it will be minus yz. So it is minus yz dx dy, and the limits are x equals to 0 to 1 and y is also 0 to 1. So the limits are 0 to 1, 0 to 1. So, but in this particular case z is equals to 0. So according to z equals to 0, this entire function will be 0. So this is the value of for this particular phase OABC. It is equals to 0. Now for the second phase DEFG, this is the value of vector f dot. Now DEFG, it is also in the xy plane but in the upward direction. So in this particular case this z is equals to 1 and it is in the xy plane, so the n cap will be k cap and ds is converted into dx dy upon mod of k cap dot k cap. So it is 1, and when we make dot product, so it will be yz, and limits are same 0 to 1 and 0 to 1, yz dx dy, and z is equals to 1. So it will convert into y dy dx. So first we take integral of y with respect to dy. So the integral of y is y square by 2 under the limit 0 to 1. So on putting the limit, it will be 1 by 2. Integral of dx. So the integral of dx is x. On putting the limit 0 to 1. So it will be 1 by 2. So this is the value for the second phase DEFG. Now for the third phase OAGF. OAGF. So it is in the xz plane. So in this particular case y is equals to 0 because it is in the left hand side and it comes from the origin. So in this particular case y is equals to 0. So we can take n cap as minus j cap and dz and ds will convert it into dz dx upon minus j cap dot j cap. So when we make dot product, then it is minus minus plus, so it will be y square dz dx, and the limits are same. Either you want to, if you want to put limit, then you can put, but in this particular case y is the 0, so the entire limit will be 0. So moving on to the next phase will be BCED. This is in the xz plane. So in this particular case, now it is far from the origin, and how much distance? This is at the distance of y equals to 1. So in this particular case y is equals to 1 and n cap will convert into j cap in this particular manner. So when we make dot product of this, then it will be minus y square dz dx, and now here y is equals to 1. So it will be only dz dx and the limits are 0 to 1, 0 to 1. So on first integrating with respect to z, so the integral of dz is z under the limit 0 to 1, so it will be 1. So it will be minus integral 0 to 1 dx. Integral of dx is x, and on putting the limit it will be 1. Minus is already there, so it will be minus 1. So for the next phase, OCEF vector f dot n cap ds is equals to double integral OCEF vector f is 4xz I cap minus y square j cap plus yz k cap, and it is in the yz plane and in the backward direction because it is from the origin. So in this particular case, x is equals to 0 and n cap is converted into minus I cap, and ds is converted into dy dz upon mod of minus I cap dot I cap. So it is 1, and make dot product. So 4xz I cap dot product with minus I cap, so it will be minus 4xz, and 4 is the constant, so we can take it outside. So double integral OCEF 4xz dy dz, but in this particular case x is equals to 0, so the value of this entire integral is 0. So now moving on to the last phase, ABDG. So in this particular case, this is in the forward direction and in the YZ plane. So in this particular case, n cap treated as I cap and x is equals to 1. So it will be the same double integral ABDG 4xz dy dz. Now putting x equals to 1 and the limits are 0 to 1, 0 to 1. So this will be z dz dy. So first integrate with respect to z. The integral of z is z square by 2 under the limit 0 to 1. So on putting limits, it will be 1 by 2, and this 2 cancelled this 4 2 times. So we can write here, or we can put here as in this particular manner, or we can directly cancel out, and the integral of dy is y under the limit 0 to 1, so the value is 1, so it will be 2. So this is the value for the last phase. So now putting all these values in equation number 2, what we get? We get double integral s vector f dot n cap ds is equals to the value are 0 plus 1 by 2 plus 0 plus minus 1 plus 0 plus 2. So it is minus 1 plus 2 is 1 and 1 plus 1 by 2 is 3 by 2. So let it is equation number 3. Now see equation 1 and 3. We can write double integral s vector f dot n cap ds is equals to triple integral v divergence of vector f dv, and which is equals to 3 by 2. So this is the statement of the Gauss divergence theorem. So we can say Gauss divergence theorem is verified. So hope you enjoyed this particular lecture. We will meet in the next lecture with a new phenomena of Green's theorem. In the next lecture, we will discuss Green's theorem. Thank you.